Hello, my name is Markus Völter and I'm going to talk to you a little bit about models in science, about mechanisms, their uses and limitations. Why am I talking about this? Over the last 10 or 12 actually years, I've been running a science and engineering podcast called Omega Tau. We've recorded 350 episodes, 358 I think is the current one, with more than 600 hours of total content. I also got to spend 1 hour in the backseat of an F-16 as a very welcome side effect of all of this. But in many of the interviews, we noticed how models play a pivotal role in science and engineering. And this talk here is based on basically the things we learned in these interviews. So we're going to talk about analytical and numerical and parametric models, forecasting versus explanation, abstraction and simplification, statistics, forecasting the past, sensitivity analysis, optimization, forecast versus scenarios, fitting of data, fake numerical precision, and the limitations from chaos, immersions, and unknown unknowns. A lot of stuff. And we'll illustrate this with cranes, pendulums, weather and climate models, flight simulators, sheep and ants, gravitational waves, fusion, the detection of the Higgs boson and its mass measurement, the Event Horizon Telescope, cellular automata, attribution science, game of life, and turkeys. All right, let's get started. I'm going to start with cranes. I've spent quite a bit of time this year photographing and podcasting about these fascinating steel creatures. And if you look closely at this picture and even more closely here, you can see there is this traffic light kind of thingy at the cap. You can see it here as well. It's more obvious here. And what does this thing do? Well, it signals the load of the crane to the outside crew. There's a similar one inside for the operator. Obviously, green means everything's fine. Careful yellow means you're approaching the maximum allowed load for the crane, and then of course red is when you're at the limit and you have to operate the crane in a way that lowers its load. And so what is the load of the crane? Well, one is the bending of the boom, right? The boom is a long stick that is of course bent from the weight that's at its tip on the hook, and of course also the stability, the balance of the lifted mass and the counterweight. So how does the crane know all of these things? Well, there's a model that calculates this and drives the traffic lights. And let's investigate what goes into that model. Well, one, of course, there's the weight that is currently being lifted. The more weight, the higher the bending moment on the boom. The length of the boom is relevant. Of course, these booms are telescopic, and if they're longer, you have, for the same lifted weight, you have or mass, you have more bending moment. The angle of the boom, obviously you can lower it and also make the angle steeper, and the lower the angle of the boom, again the higher the bending moment because the radius is larger. There are additional wires and poles you can use to stiffen up the whole construction, and if you have those installed, then your bending moment is less for a given lifted weight. And finally, wind, because if the wind moves your lifted mass sideways, this leads to sideways bending of the boom, which lowers the overall stability. So that's for the bending. For the balance, obviously the relationship between the lifted weight and the counterweight and their respective radii is relevant. So that is something that's taken into account. And the distance/radius of the stanchions. The further out you have moved them, the bigger is the, if you will, footprint of the crane and the more stable it stands. So these two aspects of overall load are calculated separately, and whenever one of them reaches a critical level, that drives the traffic light. So how is this done? Well, for the stability, for the balance, we simply use the lever principle, right? So you basically calculate the two moments. The actual lifted weight is measured from the pressure in the hydraulic cylinders. The counterweight is configured, and then the two radii. You can calculate those as well from the angle and the length of the boom, and then you can just simply figure out whether the crane is stable, the balance is in balance. For the bending, it's a little bit more interesting because here what you basically do is you run an FEM analysis, finite element analysis, where you basically simulate every little discrete piece of boom material and run a numerical simulation, a numerical model that figures out where the load is high and when it reaches a limit at any of these discrete small finite volumes. And of course you can't run this in real time in the crane, which is why the results of this analysis are abstracted into basically lookup tables, right? This is called a parametric model. We'll get back to these model categories later. But that's basically how it works. And so there is an interesting thing that happened this year, or maybe it was last year. This is a 750-ton crane, the LTM 1750-9.1, manufactured by Liebherr. And again, it can lift 750 tons. Well, it was able to do 750 until earlier this or last year, because now it can do 800. Only because of a software update. Nothing changed in the actual construction of the machine. In fact, existing cranes can be updated retrospectively. So how does this work? Well, there's something translated from the Liebherr website. It says, we completely recalculated the crane. More and more precise FEM models, on faster computing hardware, permit a less conservative approach. The latest regulations regarding the load-bearing capacity in compliance with all the applicable standards, blah, blah, blah. So basically they have newer modeling tools, both in terms of algorithms and software and machinery, computers, and now they can be a little bit less pessimistic, conservative about what the crane can lift. And so the software update basically installed new lookup tables, and now the same machine can lift 50 tons more. Regarding the balance, I talked to a bunch of crane operators this year, obviously, and one told me, today it's basically impossible to knock over a crane, to bring it out of balance so that it actually falls over. Oops, this is from 2013, where one of these large Liebherr tracked cranes fell over in Brazil during the construction of their Olympic stadium. And the problem there was surface stability, right? So the ground gave in. These cranes produce a significant pressure on the ground, and if the ground isn't suitably prepared, then the whole thing falls over. And obviously the model that considers, as we have seen, the levers of the weight and the counterweight can't know about this. So this is a problem. Here's another example of something that went wrong. A large shipboard crane in Rostock, Germany, completely crashed. And so again, is this a modeling problem? Well, no, not really. It was very likely a material fault, a production mistake in the hook itself. The hook broke, and then the whole boom basically snapped over backwards, completely destroying the crane. Millions of money lost and several people hurt. Big drama. So what can we learn about this? We have to be really careful about what goes in a model. The model sounds trivial, but the model doesn't make any statement about whatever hasn't been put into it, like, for example, the status of the ground or the material quality of the hook. And these assumptions and constraints must be well defined, and they must be communicated to the users. So is this a useful model? It's a Lego, it's a Lego model of one of these LTM 1750 cranes. It's not useful for understanding the load capacity, because obviously the Lego has no relationship to the real thing in terms of stability. But you can explain in principle how the crane works, with stanchions and telescopic booms and stuff. So it can serve as a model for illustrating that. It might serve as a model for worksite planning. If you have the worksite in the same scale, then why not, right? So this model also has its purposes, but it's not the same purpose as these mathematical models that we've talked about before. So again, the user of a model has got to know what's in the model, what the purpose is, and the modeler has to decide what is important, what impacts the results. So let's define the notion of model. It's an abstract representation of something that exists in real life, in the real world, expressed in a suitable language like chemistry, physics, math, Lego, should be an O, not A, for the purpose of understanding, prediction, optimization, proof, or production of that real world thing. The proof and production part we'll ignore in this talk. We're going to look at understanding, prediction, optimization. So when you build a model, you have to think about what part of the reality you want to represent in your model, what is relevant to represent that part faithfully in the model, how to represent and compute, right? I mean, you have to somehow make it, quote, runnable, mathematically calculatable, or in other ways executable. You have to think about how do you observe parts of the reality that serve as input to the model, and then what is the relevance and trust of the output. Again, if you don't input something about the ground, then, if you can only measure that unreliably, then the relevance of the output and the trust level of the output is low. We'll get back to that. So let's revisit analytical, numeric, and parametric models. Here is a very simple analytic model. It's a differential equation of the movement of a pendulum, right? It basically says that the angular acceleration, which is what the left term says, basically depends on the angle itself, on the sinus, on the sine of the angle, and then you multiply it basically by the fraction of the Earth acceleration and the length of the pendulum. And so an analytical model is basically where you use precise or approximate equations, as we'll see this one is approximate. And then for dynamical systems, these are often differential equations which relate a quantity to its first or second or whatever a derivative. Again, here it relates the angle of the angle phi to the second derivative of that same angle. And so again, an analytical model is what we all know from school as formulas, equations. Now, a numerical model is more interesting because it in practice plays a more relevant role for what we hear about models today. What you do is you discretize your world. In the finite element analysis we saw in the context of cranes before, you basically discretize the overall boom into finite small volumes of steel. In climate and weather models, you discretize the atmosphere into volumes of air. If you do epidemiology, you have subsets of the population. And then you reassemble the overall system by basically joining all these little volumes and computing a whole bunch of properties for each of these. I call these properties E for Eigenschaft. Sorry, I should change that. The properties. And you then, again, from the calculated properties of each of these small volumes, you reassemble the overall story. So, and then you also typically, if this is a system that evolves over time, you iterate over time, right? So again, for the weather, you have small volumes of air, you calculate various properties for each of them, and then you run this thing over time. There's a bunch of constraints. One is that you have to make sure that the changes are plausible both in time and space. What I mean by that is if you have a weather forecast and it says, at time t equals 1, the temperature at some location is 20 degrees, and 10 minutes later it's 10 degrees, there's probably something wrong. Same is for spatial plausibility. If you have 10 degrees in Stuttgart and 20 degrees in Esslingen, a city nearby, it's probably strange. So you have to make sure that either by design, the model doesn't jump both in time and space or whatever other discretization dimension you've used. Or if this is an outcome, then your model is wrong if things jump. So basically, you still calculate with equations in numerical models, but these are discretized and often spatially and temporally. These are the most obvious discretizations, but of course, others might be used as well. If you use smaller boxes, smaller discrete volumes, you get higher resolution. Same if you use smaller time steps. So this gives you increased precision. In some cases, it gives you correctness. For example, in control theory, if you have too large time steps, you might not get a control algorithm that is stable because of its large time steps, it can't see oscillations and control those. So the algorithm isn't just imprecise, it doesn't work if you don't use a fine-grained, high-resolution time. Same thing in some cases for space. If you want to forecast thermals, the stuff that propels gliders up, warm air rising above mountain peaks, and you have a coarse-grained resolution of your terrain, then these peaks are averaged out, and you will not be able to produce correct predictions of how and when thermals develop above those peaks. It's something glider pilots know very well when they fly in mountainous areas, that the forecasts are often wrong. And then, of course, the drawback of a higher resolution is that you need more computational power. And even today, with faster and faster computers, it's still quite plausible. I mean, scientists still have to make lots of compromises in various ways, for example, in resolution, to make it feasible to run on existing machines. And then, of course, you can compose these. For example, the ECMWF, the European Center for Medium Range Weather Forecasting, runs a worldwide weather model. They use 9 by 9 kilometers horizontal resolution and 500 meters vertical resolution. Up to 80 kilometers, by the way. And then the German Weather Service, the DWD, they have a higher resolution model, but only for Germany. And basically, they use the more coarse-grained model from the ECMWF as a boundary condition for what the and also a means of initializing data for the finer-grained model. And by the way, weather models calculate around 50 of these properties. So lots of stuff going on there, and so you can see easily why even large computers can be utilized completely with this approach. So let's look at parametric models again. We look at cloud formation. You can see a beautiful picture of clouds here, and the question is, what kind of cloud forms, how much of the sky is covered by clouds, what is their lower and upper limit called base and ceiling. And there's a lot of parameters that go in, right? The position of the sun, basically time of day, how much high clouds you have that limit the energy imparted by the sun. Then, of course, humidity, pressure, temperature, properties of the ground, the elevation of the ground. And so if you want to compute this algorithmically, there's lots of chemical and physical processes going on. Some of them are theoretically not even known. Lots of small things happening, lots of complex interactions. So basically, what you do in principle, again, is you discretize and you associate all these interesting properties with each of these discretized air volumes. But you can't really run this as a numerical model because, again, some things aren't known, interactions are complex, it would take too long. So what do? You basically put all these things into a series of lookup tables, right? So, for example, properties E1 and E2 from, let's say, observations. And from those, you calculate some property X. And then this property X, together with properties 3 and 4, you put that into a simple equation, which gives you a property Y, which you then use in another lookup table together with property E5, and you get the result. So this is basically a very simple lookup table and or set of equations. And of course, those are, as we've seen with the crane, filled by numerical models, analytical models, and experiments, right? Experiments, even if you don't know how something works, you can easily just take the experiment results and package them into a parametric model, which you then run to make a forecast. Another example of a very simple parametric model comes from medicine. This is actually the only software example, I think, in my whole talk. I built an application in the healthcare domain not too long ago where, for example, from the systolic and diastolic blood pressure, depending on the ranges they're in, you calculate a risk factor which you then use, for example, together with the age and the weight of the patient to make further decisions regarding treatment. These different kinds of models can be combined. in my opinion, a very impressive example is the DCS Heat Blur F14 simulator. This is a screenshot from the simulator, as is this one. Amazing visualizations, by the way. But we want to look at the flight control system and its model. So let's say we're Top Gun, right? And you know, the guy in the back, actually this is wrong, right? I should say, hey Maverick, let's turn right. So it's Goose speaking and says, hey Maverick, let's turn right. So Maverick, you remember Top Gun, I hope, you know, slams the stick to the right. What happens then? How fast does the airplane roll into the turn? So how is this done? So in the simulator, by the way, that runs on your PC. So you move the stick. This is translated into an input into the flight control system. So basically the stick angle is basically translated into a number between whatever 0 and 1. Simple calculation. Then you take the status of the hydraulic system, because that is what operates your aerodynamic surfaces. And the hydraulic system might be completely operational, but it might also be degraded because, you know, somebody shot away something or whatever. So they take into account the hydraulic pressure and then again calculate the deflection of your, in this case, spoiler and elevons. And then taking into account what the current flap setting is and what the wing sweep angle is, they use a lookup table to come up with the differential aerodynamic lift coefficient of the, you know, basically left and right half of the airplanes. And these tables, they have been, this is a parametric model, right? And they have been filled by wind tunnel experiments, which of course weren't done by the simulator developers, but by NASA decades ago. And then once we have this once we have the lift coefficients, we can take the speed and also, by the way, the air density that is given to you from the simulation engine, and you calculate the actual force that basically tries to turn the airplane into the turn. And then we also know we have to basically work against the inertia of the airplane, and the inertia is governed again by the wing sweep angle and by the amount of fuel in the wing, right? If you have been flying for an hour, you have less fuel, your wing is lighter, and so the inertia of the airplane against roll is lower. They know the amount of fuel basically from what you've filled in initially, and you know, the engine simulation tells you how much has been consumed. There's an engine simulation. And then all of this is taken together, and then they actually calculate a roll moment, and that is what is then effectively output to the user. So it's really interesting how I was going to say a stupid game, but actually DCS is a rather serious simulation. How complex the calculation is, a mix of analytical and parametric models. Obviously, numeric simulations, when you try to do computational fluid dynamics or something, would be way too slow. That doesn't work. Models are also important in the control of actual airplanes. This is an A320 landing in Stuttgart. A nice evening. So an A320 is a fly-by-wire airplane. And so the pilot doesn't actually fly the airplane in the sense that a stick movement directly impacts, let's say, directly goes onto hydraulic cylinders that then deflect aerodynamic surfaces. Instead, the pilot flies a model, literally, a mathematical model that basically knows how the airplane should behave based on the pilot's inputs. And then there is a second model, which is populated, or that is basically controlled by actual measurements. That the airplane knows its speed, it knows its attitude from various sensors. And so we have the model flown by the pilot that changes its, let's say, state based on input. And we have the model that is measured. And now what the control algorithm does is it tries to minimize the difference between the model, the set model that the pilot controls, and the actual model, which is what is measured. And based on this difference, the computer decides which control surface to use, how far to use them. If one of them is defective, they uses different ones. Very clever. So again, a model is directly used to control the airplane. So let's revisit and then close this section. Analytical, numerical, and parametric models. An analytical model is one where every value, that is a function of a bunch of inputs, can be calculated directly, right? There is no dependency on previous models. On previous values. The quantities are usually continuous, and the equations we use are usually directly the physics or some simplification thereof. And also, by the way, it doesn't have to be physics, can be any other mathematically describable thing. In numerical models, we discretize the world and we then iterate. So each result of the model that depends on a bunch of x1 through xn inputs depends on at least one of the previous x's, right? So there's a stepping through time thing. So the calculation is much more complicated. The quantities are discrete. That's what we've seen with these, boxes of air and stuff. And the equations are still basically the physics, but again, discretized and simplified to some degree. For parametric models, these values f, depending on the various inputs, can be calculated directly, but they're not really calculated. They are looked up in tables or kind of, quote, faked with very simple equations that basically encode the tables, right? So the quantities are typically ranges, and the equations or tables are not necessarily physics. They're just ways of getting from input to output without claiming that these, in the result they represent the physics or whatever it is, but not in the mechanisms. So this is the difference between the three, and all three are used. Ideally, you'd like to use analytical, but often things are too complicated mathematically, and you have to go to a numerical model. So from this discussion about parametrization, we can nicely segue into this prediction versus explanation business. So let's say we have some kind of impulse. Something changes in the real world, right? And as a consequence, the real world somehow, changes based on this changing input or this event, right? So the model approximates that input somehow, in this case as a step function. It senses it as a step function. It's input into the model, and the reaction is simulated. Some output is simulated somehow. That's fine. That's a prediction, right? So the model expresses how reality will change to some degree, approximately, right? Now, an explanation is a little bit different because it explains the why. Now, an explanatory model is one where the model embodies some kind of more general theory, like let's say Newton's laws or quantum chromodynamics or Darwin's evolution, and as part of making its prediction, the model somehow configures its internal, setup in a way where if you investigate that internal setup of that more general theory, you can understand something about why something happened, about the mechanism, how something worked. So this is a more useful model because it doesn't just make a prediction. It also explains why that prediction is the case by configuring basically a more general theory. That's a rather abstract concept, but it's very useful. And basically, again, if you look at the example of the cloud formation, which is just a bunch of lookup tables drawn from experiments, if it predicts, 4/8 cumulus in 2000 meters, and you want to figure out why that's the case, that the model doesn't help you at all. If you have an analytical model, you can see how the formulas are configured to make that thing happen, that prediction happen. So ideally, you want explanatory models. Parametric models are usually not explanatory, whereas analytical models are, and numerical models, depending on how they're built, can be. So let's look at the ultimate example of a non-explaining model. Neural networks are really the ultimate form of parametric models, right? As you know, I think, I hope. These are built from layers and layers of weighted connections. These weights are just numbers, and they are learned by the model during the training phase. And, from a prediction of a neural network, you just have no clue why that's the case, because these millions of weights have no actual traceable connection to reality. It's not transparent what effect each of these parameters has and what the model has learned. So there's a nice example where the idea was to build a model to detect sheep, right? But what it in fact did, sorry for the German words, but I think they're close enough to English, it basically picked up on the green grass. So when you showed only green grass to the model, after it has learned, it also predicted sheep, right? Because it didn't, again, hook on the sheep, it hooked on the grass. So because you don't know what these models learn, I mean, there's ways of limiting that risk, but still, it's very hard because there is no explanation as part of it. You'll get a wrong result with some probability for situations the model hasn't seen before. And you can't easily find out what it has seen before except by tracking training data, but then you have to be sure it's complete and, hard. So it's not a big problem for advertising, right? If you get, yellow shoes advertising, even though you hate them, doesn't really matter, it's annoying. It's a bit more of a problem if you are not allowed to get a credit because the model made some stupid assumptions about where you live and generalized in a way that is not fair. And it's really fatal in autonomous driving, right? If the model doesn't recognize correctly dangerous situations and makes a wrong decision. So again, these parametric non-explanatory models are limited in their use case. They do predict, hopefully, but only with some probability and for some scope. So let's look more generally at abstraction and simplification. Again, back to this pendulum. How quickly will this thing pendule back and forth? I know pendule is not a word, but I think it's funny. Actually, the period of a pendulum is rather complicated. I copy and pasted this formula from Wikipedia because I was didn't want to type it up. It's even too big to type. Now, we don't have to look at this in detail, but you can see that the period depends on the actual angle, right? So basically, if the angle is less, the period is probably faster. I don't even know. We can make a simplification where if we only take into account small angles, where sine of x is basically the same as x, as you know, the sine function starts kind of as a more or less, as a straight line for very small x, then the period is simply considered a constant and depends only on the length of the pendulum and the Earth acceleration, gravitational acceleration. So that's cool. It's easier to compute, obviously, but it's restricted, right? It has, it's only valid in small angles, and if you use this model outside of the range where the simplification sine x equals x is valid, then you get wrong results. Another question, will it oscillate forever? Right? If you look at the formula, there's nothing obvious how, this might change. So you get, this is basically a formula that has no damping whatsoever. If you get damping, for example, from internal friction of the material or aerodynamic drag, then the amplitude of the pendulum will get lower over time, and at some point it'll stop. So probably for your, Kuckucksuhr pendulum clock, it doesn't really matter because you re-energize it every day anyway, and it's not an ultimately high precision device in the first place. But if you want to use pendulums for detecting gravitational waves, the situation is different. So let's look at gravitational wave detection. As you know, in 2016, the LIGO detector has heard gravitational waves directly. This is from the Astronomy magazine screenshot here. And again, the gravitational wave is something that can be shown this way. What this shows is time on the x-axis, so basically how the wave changed over time. the frequency of the wave, and then the intensity is represented as the darkness here. So you get something that takes about half a second. It increases in frequency and it becomes louder. So it does something like rup, rup, something like that. So it's like a bird's chirp. Anyway, so how do these detectors work? Well, they basically send, I say basically a lot, I'm sorry. They send a laser beam along an interferometer in two directions, and then they interfere the two laser beams. Normally, these two arms here have the same length. So this means that the laser shows up with the same phase at the output, and if you interfere these two, you get constructive interference. So you get a certain interference pattern. Of course, you can also set it up so that it exactly destructively interferes, but it doesn't really matter. On the two, and then if a wave comes by and makes one of these arms longer and the other one shorter, then the relative orientation of the phase changes and you get a different inference pattern, right? That's how these things work. Now, problem is, of course, these mirrors here, they have to be very, very, very quiet. If they vibrate because of, I don't know, air movement, a truck that passes, next to the detector, you get screwy results because you detect other crap and not basically vibration from the gravitational wave. So these mirrors are mounted on multi-step pendulums, which mathematically produce a really, really high degree of vibration isolation. There is also active damping with magnets, and there is also, you have to understand exactly the behavior of the laser and even things like shot noise. So you have to do a lot of work to understand exactly how this pendulum, and that's the connection to the previous example, is dampened, because otherwise you cannot understand how this thing moves and you cannot understand how quiet it is mounted in order to detect distortions or the truck that drives by from the passing of a gravitational wave. So all models are simplifications. How and how far you simplify depends on the model's purpose. Let's look at another example from the Wendelstein 7X stellarator fusion experiment in Greifswald, which I visited, I think, in 2018. Don't remember exactly. Did a great podcast about that. So how do you model the plasma in the reactor? The plasma is where the fusion happens. There's various different ways. You can represent it basically as a fluid. This is then called the magnetohydrodynamic representation. You can also model it as a mix of two gases. One would be the electron gas, and the other would be the gas that forms from the cores of the hydrogen. In this case, I think I forgot. And so you use kinetic gas theory to model that. You can also go much more detailed and model each of the particles, like of the, let's say, electrons and protons, neutrons probably then. But because of the magnetic situation in this reactor, they move on small circles. But you can forget this small movement and model this simply as a disk, or you can actually resolve the movement of these circles around that disk as a consequence of the magnetic fields. And of course, it's important that all of these models for their respective applicability ranges produce the same results, even though they simplify in different ways. So again, they use all of these, and depending on what they want to do, and we'll get back to that later, they use a different, or they select which of these representations of the plasma they use. Let's look at statistics in the context of modeling. You've all probably seen this diagram. It's a sketch of the Large Hadron Collider. The big ring is the Large Hadron Collider. The other smaller rings are accelerators from previous generations, which are still used as pre-accelerators to boost the energy of the particles before they enter the big ring. And you've all maybe seen these huge detectors. This is, I think, Atlas. Yes, it is Atlas. One of the detectors that once particles collide in the big ring, track the particles that spew out of the collision. Again, this is our Atlas. There is also CMS and Alice. Atlas is the largest by volume. CMS is a bit heavier. So again, this is how these detectors look. The collision of the particles of the two beams happens in the center, and then these detectors have various detector components that are able to see different kinds of particles. And you can see the people here to give you an appreciation of the size. I visited Alice at some point. It's really impressive. So here is a picture of one of these collisions. You can see a bunch of detector elements around the collision that are highlighted because they detected something, and you can see the particles spewing out. So this one here is a screenshot from, again, Atlas, or picture from Atlas. And it says that what happened here is that two protons collided. They formed a Higgs boson, which then decayed into two bottom quarks and a W particle, which decayed into a neutrino and a photon. How do we know, right? How do we know this? And how do these detectors work? So basically what they do is they have a huge magnetic field, and then they measure the amount of bending of the created particles in that field, because that bending depends on the particle's momentum and on its electromagnetic charge. And then different kinds of detectors are engineered to see different particles. There are silicon trackers, there are electromagnetic calorimeters, hadronic calorimeters, muon chambers, and as you can see, different particles make it further out and then die in various different detectors. And so each of the interesting particles produces a unique fingerprint, basically, in these detectors. And then again, you can measure their bending. So this gives you the kind of particle, and then you can use the bending radius or the amount of bending to determine their momentum. And then you have basically kind and energy, and this combinations are unique, and then you know what's going on. So basically, in this case here, your Higgs boson decays into various other particles through various paths, right? The A, B, C, D, E are just random names. I didn't even bother in this example to use the correct particle names, not important. And then that's what the detector sees, right? The detector sees the results of these decays when they impact into the various detector surfaces. So that's what's called the final state. But what we're interested in really is the initial state. What happened originally to produce that Higgs boson before that boson decayed into all this other crap? And so that's where the scientists come in. Einstein has nothing to do with it. To basically calculate the initial state, what happened physically from the observed final state. And that is not so simple. In Germany, we say there is ein Haken an der Sache. That's why I have this hook. It doesn't work in English. Sorry. So basically, first of all, the Higgs decays in many different ways. It decays into two bottom quarks, or quark and an antiquark, into a positive and a negative W boson, into two photons, and the various decay paths have different probabilities, right? So you have to untangle those, because in the end they all become the same, set of particle zoo. Again, photons, electrons, muons, hadrons, and so you have to disentangle these different processes that all happen at the same time. Decays are non-unique, right? So this E particle here, the simplified case, can either in this example result from Higgs to B to E, or from Higgs to A to D to E. So again, if you see an E, it's not unique. You have to somehow use, again, statistics to find your way back. The collision energies are not known necessarily. You can have soft collisions and hard collisions in which the protons are destroyed, whereas in soft collisions, they're just basically, their path is changed. So that makes it more complicated. And of course, the detectors are hugely complicated devices, and they have imprecisions, and you have to somehow take those into account as well. So how do they know what they're observing, and how do they know that with 5 sigma? Sigma is basically a measure of the trust. It has something to do with standard deviations. We don't have to go into too much detail, but 5 sigma, the border for a physical discovery, means there is a probability of 0.000057 something percent that whatever has been observed happened by chance and not by whatever theory predicts it. This is also related to the p-value that is used, for example, in medicine for determining the trust in studies. Without going into too much detail, medical studies don't get anywhere close to 5 sigma. It's like they're happy if they get, whatever, 5%. So it's impressive how far physicists go. So how does this work? Well, statistics, right? They simulate billions of events to understand the distribution. They simulate billions of events. So they have basically a so-called event generator. It's a model of the physics. It's a model of how particles decay depending on energies and other variables. This gives you basically a simulation of what happens during the collision, which leads to vectors of particles streaming out. This is then piped into a model of the experiment of the detector. It's called GANT4. So this gives you a result of how these particles interact with the detector surfaces themselves. And then there is also a model of the electronics that simulates how noise impacts the measurement. And ultimately, this gives you simulated raw data, right? So millions of these simulated collisions are run, taking into account known physics. In the case of Higgs boson, no Higgs boson. This gives you then a lot of data of without Higgs, and then you take the actual measurements and you compare them. And then in the case of the Higgs, for example, you can see there is a difference between the prediction without the Higgs and the actual measurement, and that difference is an energy peak at 125 giga-electron volts, and you do this then often enough with a bunch of math to make sure you have your 5 sigma of trust. So again, you do thousands of measurements and millions and billions of simulated collisions. Of course, they do also billions of collisions, but only some of them are, have the right energies and the right setup so that they're relevant here. And of course, lots of computing going on. There's millions of lines of code developed over decades that run these simulations. Fortran, of course, and Python for wiring the infrastructure up. And there is terabytes of data, and all of this has to be distributed and scheduled to do all the calculations and simulations. It's a huge computing infrastructure going on here. So how can we build trust in models? Well, one way is we do experiments with lots of data and some statistics to verify these experiments. Now, experiments basically means you have controlled conditions. You can prevent, interference. You can therefore isolate influencing factors, which means that you can distinguish correlation from causality. You want causality in experiments, but you want to understand which things are merely correlated. But sometimes experiments aren't feasible. Like you can't experiment with the climate, even though people say we do, right? It's a different story. But you can't actually have an experimental planet next to us to run experiments. Same in epidemiology. You can't really experiment at large scale. Economics, many societal questions are the same way. So you have to just observe. So in observations, you have no controlled conditions. Stuff just happens. It's very hard to isolate influencing factors, and therefore you basically get correlations, and you can attempt to explain causality. So natural experiments sometimes help. You have, for example, economic stuff going on in many different countries, and you can try to statistically isolate influencing factors, but it's generally much harder. So what can you do? Well, one thing is you can reforecast the past. Let's say you want to do a weather forecast, and you have a parameter that, for example, represents how clouds form, right? Getting back to the previous example, and you don't know what that parameter is, right? You want to tune your model to use the right P to make a good prediction. So what can you do? You can reforecast the past, right? So you can go back in the past. You can, run your forecast from a point in the past, because from that point to now, you do have actual data. So you can compare. You can tune your parameter P. You can give it some value P2, whatever that is. And then you can use that value to make the actual forecast into the future. And that's actually done in forecasting all the time. So these weather models are tuned all the time, and one way of doing this tuning is by reforecasting now known data from the perspective of the past. So reforecasting the past is one way to build better models and thereby increase the trust in those models. But as we said before, all models are simplifications. How far depends on the model's purpose. Which parameters are relevant? How do we know which parameters are even worth investigating and getting right? Well, sensitivity analysis to the rescue. Let's say we have a model M. It's probably a non-explaining model, and it has a bunch of parameters that we have to tune, P1 to P3. How can we figure out which ones are worth putting into our model and measuring precisely? Well, we can scan through all of these parameters and then see which of them has a significant impact on the result. And in this case here, we can see from the length of the bar for P3 that parameter P3 is relevant. The model is said to be sensitive to P3. Opposite, by the way, is robust. And this means that we have to either measure and determine P3 very precisely, or if we can't do that, because there's no way to measure it, for example, then whenever we make a forecast, we have to always vary P3, and the model then only predicts a range of outputs, because again, we don't know exactly which of these P3 values is relevant. Ensemble forecasting is used in weather forecasting here. It's a method where instead of making a single forecast of the most likely weather, a set or ensemble of forecasts is produced. And then this set gives an indication of the range of possible weather situations. And these parameters we're talking about are, one, the initial conditions, because you can't measure the actual weather for the whole planet. There's lots of places on the ocean where there is no way to do that, although this changes through satellites. And then also the parameterization of the model itself, again, this example of cloud formation. And then, again, you run the model from the initial conditions. You, for example, take you vary your temperature because you don't know it precisely, and then you run the forecast, and it gives you a distribution of possible weather outputs, and you might either communicate the whole distribution, or you take the probability peak as what is your forecast. There's a very nice service, MeteorBlue, which is weather forecasting service, but as you can see here, the Treffsicherheit der Wettervorhersage ist mittel. The reliability of this forecast is medium. And then what they do is they run a whole bunch of, you yourself as the end user, you can see a whole bunch of models for your place you're interested in. And it gives you even a verification of how well the various models have forecasted the past. So nice, because this makes this uncertainty transparent, which I think is nice. Many models should do that, right? They just shouldn't just forecast or predict some kind of value. They should explain to you how trustworthy it is and how they got there. There's another nice example of this sensitivity analysis, and that's in epidemiology, one of our currently most relevant topics, of course. So basically how a virus distributes is basically simple, right? It's exponential growth. So, this exponential curve that depends on basically this R factor that we hear about all the time. But it's not quite as easy, because most exponential growths are actually logistic growths, because at some point there are limited resources. In the case of the epidemiological situation, at some point everybody's infected, right? And then things don't grow any further, or more precisely, we reach herd immunity? So one of these interesting questions here is at what level of infection of the do we reach herd immunity, or how many people need to get infected, or what's the ratio of people that need to get infected for the virus to not spread any further? By the way, they might not have to get infected, they might be immunized through a vaccine, but same story. Basically the person is not available to the growth of the virus, the distribution. So now there's a system developed by Explosys, it's called COVID-Sim, that lets you simulate all of this. Of course, it's not quite as simple in the real world, right? So here is a bunch of differential equations that are used by a previous version, actually, of COVID-Sim. So you can see there's a whole bunch of different equations, and actually, if you zoom out, there's a whole bunch more, and a lot of parameters that need to be tuned. So getting all of this right really isn't quite as simple as just a simple logistics growth formula. And it turns out that the resulting herd immunity, the minimum infection rate we have to get to achieve herd immunity, depends on how you model the age distribution. It's not that it depends on the age distribution in your population. That's obvious, right? Because differently aged people behave differently and stuff. But it depends on how fine-grained you group these age groups, right? So who'd have thunk? So I know that I talked to somebody who builds these models, and he said that that's not something they expected. So now you have to make a decision. How fine-grained do you go? So again, it's a question of model tuning, and you can do this through sensitivity analysis, and that figured out that the age group grouping is relevant. In analysis fusion, there is also a nice example here. So let's say we want to optimize the distance of the plasma from the reactor wall. The plasma is very hot and you don't want it to touch the reactor wall because, not that the reactor wall will burn up, but the plasma will be destroyed or at least negatively impacted. And so you can, for example, increase or decrease the magnetic field that stabilizes the plasma. You can change the gas density, the number of neutral particles that are injected. There's a bit of fusion detail, or you can change the temperature of the plasma. And all in all, there are 10 to 100 combinations which you potentially have to numerically iterate through. And so the question is, which of these representations of your plasma do you use? And in this case, of course, they use the fluid representation because that's the most efficient for computation. And luckily, it gives you a good result. And so basically, it's a huge sensitivity analysis that is run through all of these parameters in order to figure out where they should spend their engineering effort. Now, of course, the point is that, again, 10 to 100 combinations, even with the simplest model, won't work. You only have 10 to the power of 85 atoms in the universe. And so that's tough. What can you do? Well, that's where computer science, math, and algorithms comes into play. You have to use clever optimization algorithms, things like hill climbing, simulated annealing, efficient solving of numerical systems. Lots of books about that. That's where the computer scientist can start to play a role, but that's outside of our presentation here. So how can we build trusted models? Well, we can vary parameters and analyze their impact, and then take that into account when we build the models. So before we move on to the next way of trusting models, I want to stay briefly with this parameter variation for sensitivity analysis, because there are two different things you can do: forecasting and scenario prediction. Not really prediction. Anyway, so let's say we have this model here with these three parameters, and we scan through, right? We see the output, and we want to do this because we want to reduce the overall computational complexity. We want to, for example, build a weather forecasting model, and we want to see which of the parameters we have to ensure to get right because they have lots of impact, but we can't afford to, to calculate all of them precisely because then we would run out of computational power. So Let's say P1 is the cloud formation depending on temperature and humidity. It's our previous example. P2 is radiated energy depending on coverage of this high-level cirrus clouds. Parameter P3 might be the amount of precipitation depending on the layering of the atmosphere, basically a convection story. So now we run the analysis, right? We figure out these sensitivities, and then once we have done that, we have a correct model, and we can, every day then measure data and use that model, and we get one good forecast. It's an actual forecast. The idea is to tell us how the weather will be, because we have now a well-tuned model. Let's look at another example. In this example, we don't really want to make a prediction. We want to really just understand the parameters. Let's say the epidemiology example, P1 is the one-to-one infection rate. Basically, it's how likely it is if, I'm in the same room with you and I'm infected with corona, how high is the virus shedding rate, and what does this mean for a one-to-one infection? P2 is virus shedding depending on the kind of mask, right? So if I wear a mask, how does, for the same amount of virus I have in me, change the virus shedding, right? And then P3, what's the 1 to n infection rate depending on the rate of interpersonal contacts? I mean, the story behind this is clear, right? It's the classical problem, does mask wearing make sense? Do we have to restrict meeting other people and stuff like that? So in this case, we want to do something completely different with the model. We don't want to predict how the real world will change. We want to understand, based on simulated data, what are useful scenarios, right? We want to understand that if we use this kind of mask and we reduce the rate of meeting other people by 50%, then we have a certain reduction in, the curve, right? The curve is made flattened. So in this case, we don't predict. So I'm mentioning this because I've heard people say, well, these models that predicted how the infection rate will change over time weren't right. Well, it's not about predicting, because you can't predict. You can't predict how people will behave. What you can do with these models is run different scenarios and say, if you behave this way, masks, for example, then it will very likely, change in this following way. So in this case, we produce scenarios which we then use for decision making regarding policies, for example, regarding the wearing of a mask. And interestingly, these healthcare models, right, the medical models, suggested a early and hard lockdown works best, because, again, if you want to win against exponential growth, it's easier to do this in the early phases where the absolute growth rate is low. The economical models said an early and hard lockdown works best because we need a shorter lockdown, and therefore the total cost is limited or less. Psychological models suggested that an early and hard lockdown works best because if you first do a lockdown light and then make it harder and harder, it's more and more challenging to get people to obey because of lockdown fatigue. They've already been for weeks or months in a light lockdown, and now it should become even harder. It's a very hard sell. So, all these three different models suggested, early and hard, but Germany starts with a lockdown light and it does it too late. So, lesson, the best models and their scenarios don't really help much if society or whoever should look at those models, doesn't take them into account. That's a statement of frustration. All right. So, how can we build trust in models? Last way of doing that, if we have an explanatory model, right? One that doesn't just make a prediction from opaque parameterization, but actually configures our more general theory, then we can take a look at this configuration and see if it makes sense. Is it plausible? For example, in our fusion reactor example, if the model assumes that the pressure of the plasma is 5 times higher than what the reactor vessel can deal with, then, it's not a very useful outcome. So, if we have an explaining model, we can check if that explanation makes any sense. So let's look at fitting from data to model. Here is the image of the black hole that was taken 2019 by the Event Horizon Telescope. You've all heard about it. It's only sort of an image. I mean, no, this is an image, but the EHT only sort of took a picture of it. So let's see how this worked. So the EHT is a radio interferometer, right? It means that it computationally combines several different radio telescopes, and then with lots of computing creates an integrated result. In this case, it combined telescopes from all over the world, in what is called very large baseline interferometry. And why is this useful? Well, the resolution you can achieve after all of this computing depends on the length of these baselines, on the distance of the elementary telescopes, and so this is kind of, there's also space-based experiments, but basically this is the largest you can get. And then, yeah, that's what I just said. And you know all these telescopes. This is the Effelsberg telescope, 100-meter dish. This one is not part of the EHT for reasons beyond this talk, but just to give you an impression of these kinds of telescopes. Many of the telescopes used for EHT are a bit smaller, and interestingly, one of them, ALMA, in the Atacama Desert in Chile, is itself an interferometer, or made up of dozens and dozens of telescopes. Very interesting engineering, but again, beyond the scope of this talk. So basically the idea is that you look at the same spot in the sky from these different telescopes, and obviously then a particular point you're looking at has a different distance to each of the observing telescopes, right? This distance d is different. And of course, if you take the propagation of light c as constant, then this distance also corresponds to a certain delta t. In other words, the light arrives at antenna 1 a bit later than it arrives at antenna 2 in this particular example. Similarly, this distance d also depends on the angle at which the telescope sees a target, right? And if you take these things together, right, the d is proportional to this delta t and is also depending on the angle, you can do a lot of math, and you come up with this formula here, which basically expresses the visibility of any particular target depending on a bunch of antenna characteristics and on an exponential term here that depends on the position in the sky. I'm a little bit deliberately vague here. In my book, you can read all of this, not important. But the point is, if you look closely at this formula, you'll see that this is a Fourier transform of the sky. So it's basically a distribution of spatial frequencies. So again, the radio interferometer doesn't take a picture. It observes a Fourier transformation of the sky, right? Now, of course, in order to get to the image, you can do an inverse Fourier transform, right? That's relatively obvious. But this frequency distribution you measure with this telescope depends on the length and orientation of all of these baselines. And now, obviously, if we have seen here, I'm going back a few slides here, we've seen that there is only certain distances and certain orientations, right? And of course, the Earth rotates, so these orientations change a little bit over time. But in the end, consequence is you cannot get a full coverage of all orientations and all frequencies. So you have incomplete data. So you somehow have to do this inverse Fourier transform despite not having all the data. And this is a non-unique problem, right? You only have 10 baselines that rotate with the Earth. And so how do you get back from the observed incomplete data to the actual image? So another more general question is, which mathematical description, that would be your image, approximates the data best, right? So this is a problem of fitting. So you have a bunch of, and this is a simplified example, of course. You have a bunch of data, a bunch of measurement points, and you want to find a mathematical formula, basically a model, that minimizes the total error. And the total error in the right picture you can see is basically the sum of all the red bars. So let's say the actual observation would be this horizontal green line. Then, if you will, the fit of that simple formula, y equals y0, is one constant, not depending on x at all, is the sum of all these red bars, and it's obviously rather bad here. So here's a bunch of other alternatives, right? You have, again, this constant, you have a single straight line, you have a parabola, and you have a polynomial fit. It is well known that if you use enough terms, you can make any bunch of measurements fit exactly on your line. But, you know, and of course the total error is 0. But is this a good idea? It's not really, because it's a so-called overfit, right? So it reproduces the data perfectly, but there's no useful prediction because if you go a little bit beyond this curve, you don't know how it moves. You have no idea if this makes any sense because there's no abstraction in here. It's not a useful model. So we can scratch that. In neural networks, you have sometimes the same problem with overlearning. Different story. Cut that out. This one doesn't work much. So then how do you decide between these two, especially the straight line and the parabola? It's not really obvious, right? So what do? Well, you take into account knowledge about the system at hand, right? Is the result useful? Does it fit with my understanding? So we're back to an explaining model of how the particular thing I'm trying to fit to works. So in this case, we look at the observation of a black hole. We know that basically at the very center, from radius 0 to the radius of the black hole, to its Schwarzschild radius, we see black, right? We see the black front side. But because of the strong gravitation, we also see between the Schwarzschild radius and about 2.6, that same radius, we also see black because the light is bent to hit the backside of the black hole, which is also black. So, and then outside of that, we have a glow of radiation that is accelerated around the black hole because of the gravitational force. So anyway, we basically expect to see black from r equals 0 to about 2.6 rs, and rs is something that is a quantity that depends on the mass in the black hole. Anyway, this can be known from other ways. And so basically we expect to see a kind of glowing ring, right? So now the problem is that if we already put knowledge about we want to see into the fitting process, we might, potentially produce a self-fulfilling prophecy. Basically, we fit in a way so that whatever we want to see is what we get, right? Not very useful. So how do you prevent this? Well, in this case of the EHT, they have 3 different deconvolution algorithms, so 3 different algorithms of how to perform basically this kind of inverse Fourier transform. They used 3 different software packages, 4 independent teams. They worked with synthetic data, which were in this case magnetohydrodynamic simulations of black holes and other shapes. So, to make sure that not every data set always produces this donut, right? If you have data that is not a donut, if you have Fourier data that does not represent a donut in the space domain, then it shouldn't produce one, right? And so that's how they did it. And of course, then you still have to minimize the error, right? So that's how they basically produce this image. So again, this is another way of saying, does the explanation make sense in the fitting process, right? You can't just fit to any crap. You have to fit to, if you will, a model that makes sense, that you can somehow substantiate from different ways. How far can we trust models? We've all seen statements like this, right? If we had started the lockdown 1 week earlier, 30,372 fewer people would have died. This is an example of what I call useless precision, because fundamentally the precision of your model's output should be somehow, proportional or in line with the precision of the inputs and the how well your parameterization is known. And clearly for epidemiology, we don't know, there's lots of factors we don't really exactly know. So this means basically there are different kinds of models. There are qualitative models that only give you tendencies, right? So if I increase some input A, then the output X will also increase. Like if we have, I don't know, fewer masks, then we get more infections. Or if we have start the lockdown earlier, we get fewer people dying, right? So this is only relationships. There are relative or comparative models where you say, well, we can say that input A or factor or parameter A influences output X twice as much as B. So even though we don't know the actual numbers, we can, from the math, we can say something about the relative influences of the different parameterizations. And then we have the quantitative models, basically numbers, right? If A increases by 10%, then the output B decreases by 33% or something, right? That is what we all want, but often this is not achievable, and we have to make do with some of the less lower fidelity models. Here's an example of fake precision in some way, although I'm not suggesting people use it this way, but it's a nice illustration. So there's a Drake equation. How many civilizations are there in our galaxy? Here's the formula. It's a bunch of factors that are all multiplied together. Things like the average rate of star formation, the fraction of stars that have planets, the fraction of planets with life that actually has gone on to develop civilizations, all of these factors, right? So now this looks like a numerical formula, but basically it's a parametric model because none of these things that we mathematically multiply here has actually precisely known quantities, right? So this is only a qualitative model, nothing else. So using an equation doesn't necessarily make something a quantitative model, right? Because it depends on whether you actually have precise numbers for all of these things that feed into the model. All right, let's look at more fundamental limitations of the whole idea of modeling. First one is chaos. A small change in some initial condition or parameters leads to a huge effect over time. So the simplest example is the chaos pendulum. You know that probably from school. We've had several of those in school. So you put it into some position, you let it go, and after whatever few seconds, the movement is completely different, even though you tried to start it from the same configuration as in your previous trial. And another example is this butterfly in Brazil, where, if the butterfly launches in Brazil, then this leads to a thunderstorm in Europe. By the way, I did talk to meteorologists and asked them about this explicitly. While of course the weather is chaotic, they weren't so sure about whether a butterfly could really lead to a thunderstorm. But beside the point. Point is, these systems are deterministic, right? We know how to calculate these pendulums. We know how to calculate weather forecasts, but the interactions, for example, the way the actual friction on these joints here and the pendulum isn't exactly known, and we don't know the initial conditions perfectly. So that's why a small change, if you have enough degrees of freedom, can lead to a large output. And of course, this limits your modeling precision or trust or fidelity, because you don't have a precise understanding of all interactions and or all initial conditions. And for weather forecasts, this is a major reason why weather forecasts only useful for 5 days maybe. Then of course this climate skeptic guy will say, how, if we can't even predict weather, how can we predict climate? You hear this all the time. Weather forecast limited to 5 days, but we claim to, talk about climate in 50 years. And of course we talk about statistical predictions there, which is a completely different ballgame. So again, let's look at the fusion reactor. We can't precisely predict and track the position of each molecule because it's chaotic, right? But of course we can say something about the average, which in this case is things like temperature and pressure, and they can be calculated precisely. There's lots of physical and chemical formula that are precise, like really precise, but they only talk about the averages. So statistical prediction is just different from tracking, potentially chaotic individual contributors, for lack of a different word. There's a very nice example from climate research as well. It's called attribution science. The idea is to answer the question is a particular weather event, extreme weather event caused by climate change. Now, really what this is asking, with which probability is this kind of extreme weather event caused by climate change at this location at this time of year? So obviously it doesn't look at one exact particular event, but about a class of events, and says something about probabilities. How is this done? Well, you take the current atmosphere, you modify the initial conditions, right? You basically scan through how much influence a slightly different weather setup would have on the outcome, right? And then you check with how many of these modified initial condition scenarios you get the extreme weather, right? Then you do the same with the current atmosphere minus the human impact. So for example, you reduce all the CO2, and the methane, that's the axis here in the example. And then you do the same thing. And then you probably get a different ratio of scenarios, ranging through the same initial parameter modifications. And then you compare these two ratios. And this gives you the probability whether the extreme weather was caused by this different setup of the atmosphere, climate change, or not. So this answers your question. There's another extremely nice example about chaos that we should look at, which is cellular automata. Because people sometimes say, well, this chaos only happens because of the imperfections of, our ability to measure something, or because we don't really understand things well. There isn't really, chaos in the fundamental science. Well, there is. Here's an example from pure math. There is no measurement imprecision going on. So cellular automata. You have a grid of cells. A cell is either alive or dead, black or white. Now, the system evolves over generations. Here, this is the vertical axis. And the generation I is somehow depending on generation I minus 1. And basically, the dead or alive status of each cell, at some coordinate x and at some generation I, is calculated through some function. And that function is characteristic of a particular cellular automaton. Here is, so basically, in this case, they always take the two neighbors of a particular cell in the previous generation into account. And there's this example rule here that basically says if all three were black in the previous generation, the next one is white, and then only if all three were white in the previous generation, the cell in the next generation is black. And so this is through some nomenclature called the rule 1. And if you run that over time, you get this alternating pattern forever, right? So you can, instead of showing this graphically, you can show that same, or just give that same thing as a formula. And this is an iterative numeric formula, right? Because it looks at the previous generation, right? And it just flips the value. But you can also give a closed representation of this, right? Here, there is no I minus 1 anywhere, because you can basically just say if you have an even row, then, there's one setup, and if you have an odd row, there's another one. So this is an analytical formula for that particular rule 1. So this rule 1 is deterministic, in other words. Now, here is another rule, rule 13. It looks like this, and it has been shown to be chaotic, right? So you can't really give a closed formula. You can, of course, give the iterative one. It's basically the, just giving the cases here. basically representing this thing as just a bunch of if then else statements, kind of. And you can run this even further, and you can see how one change in the initial condition has a huge impact all through. So this really, you can't give a closed formula. It's Stephen Wolfram calls it computationally irreducible. It's actually a very good random generator. It's chaotic. So here we have an example of chaotic behavior in pure math. So chaotic is a fundamental characteristic of certain systems. It is not just a consequence of imprecise measurement, although imprecise measurement or knowledge of parameters is a reason for effectively leading to chaotic behavior. Another thing that limits the ability of models to predict is emergence. We all know that ants have rather sophisticated aggregated behaviors, but each of them probably doesn't have a huge brain to make sophisticated decisions. So how does this work? Well, the idea of emergence is that you have a bunch of agents, right? They all follow very simple and well-defined rules. And then you have many interacting agents, and they interact with different, let's say, interaction patterns. And as a consequence, you get some kind of complex result. And the point is that you cannot predict the complex result by observing and understanding the simple rules, because you can't really understand how these interactions happen. Now, it's interesting that ants are this way, but there's also lots of this stuff going on in our own world where politics tries to set some simple rules. And then we, as a society, we interact in a complex way, maybe game theoretically to our own advantage. And then the outcome is unclear. So lots of societal, economical, and social systems, also if you combine them with technology, have this characteristic of producing emergent behavior, which is hard to predict. So what can you do with modeling here? Well, again, you model the rules for the agents, and then you just run through scenarios, lots of them. You modify certain inputs from time to time or certain constraints, and then you get outputs, and then you look at them with humans. You specifically investigate these, and then maybe you find, oh shit, there is this kind of corner case that people try to exploit. Let's change the rules a little bit to try to make sure that this doesn't happen. And then you run another 1,000 simulations and still see whether this still happens. There are people who do this exact kind of agent-based scenario simulations for socio-technical systems, for example, how energy systems interact with society and stuff like that. Very, very interesting. It's also a nice concrete example. The Berlin government tried to limit or reduce the rent people have to pay for apartments. The idea was a simple rule. We define an upper limit for rents. The idea would be that rents would be lower, less affluent people would find apartments. What actually happened is that 37% more apartments were sold because people weren't interested in letting them. 28% fewer apartments were on the market, and 200% more inquiries per apartment occurred. And there was even a shadow rent that people had to pay for the case that this whole law isn't compliant with the German basic law, German constitution. So ultimately failed, right? I'm not saying this couldn't perhaps been predicted, right? But certainly the simple rule didn't have the intended effect. It's a case of emergent behavior. You have to take all the interactions into account. And again, this is hard. I'm pretty sure they didn't run agent-based simulations to figure this out. Another example of emergence comes from pure math. There is Game of Life. It's basically a 2D cellular automaton where, depending on, in previous generation, how many of the cells around you were alive, you as the current cell will die or not. If there's, if only one was alive, then less than two were alive, you die from loneliness. If it's either 2 or 3, then it's a kind of healthy environment and you survive. If it's more than 3, you die from overpopulation. If it's exactly 3, then you reproduce. Actually, there's a mistake here because 2 and 3 doesn't work, but you get the point. Here's something interesting. Shit. In the preview of PowerPoint, this doesn't move. So these things here, if I would show the full, the PowerPoint presentation mode, these would actually move, almost like they would coordinate. They're called oscillators and glider guns and spaceships. These are fancy names for these things. So the point is there is emergent coordinate behavior from simple rules in pure math. So again, it's a fundamental property of our universe, and I'm not even talking about probabilities in quantum physics and stuff like that, but it's very interesting that this emergence is not something that is just, again, a consequence of our inability to understand something. So what can we do, right? Well, we can define a new set of rules for the system as a whole, right? So we observe these systems, and then we basically jump up one level of abstraction, and we don't look at how an individual ant behaves, but we say, a typical ant, what's called family, state, country, whatever, typically on average behaves in the following way. And so we can, again, make predictions on this aggregate level because, of course, we can observe the emergent behavior and, if you will, build a parameterized model for that, but we can't predict it from the rules. And this is a very general idea, right? If you want to understand these ants, again, you can't go back to biology because this would be the simple rules. And if you go back further, try to explain it by chemistry or even by physics, it's a lot of work, doesn't really work. So you build higher and higher abstraction levels that make sensible statements for the level of abstraction you're interested in. And that's basically how modeling attempts to work, right? So abstraction allows us to tackle aggregated complexity. There is a nice statement by Edgar Dijkstra, a very well-known computer scientist. He said, "The purpose of abstraction is not to be vague, but to create a new semantic level on which we can be absolutely precise." I think this is just so perfect. This exactly describes why we abstract and why we build models that are potentially simpler or leave out details. As another example for something that makes modeling complex, which is path dependence. Let's say there is this whole complex world and we ended up on this point out there. How did we get here? Well, we get here because of all the random context, resource dependent, cultural, political decisions we've made on the way here. It's a complex evolution over time, right? So we can't predict where we will end up except by going the path. If we go, this is a nice example, if we were all, destroyed, or the civilization was killed by some kind of, cataclysmic event, and only, few 100,000 people survive, and they have to rebuild civilization, they will not produce an environment with climate change because they probably don't have any fossil fuels to burn, right? So the reason why we produced this climate change was in some sense accidental, because as it happened, we had these fossil fuels available to us, and at least initially we didn't figure out that this would produce climate change. So simplification really doesn't work. You just have to go the path. And again, evolution itself of humans and animals is an example of that. There's a good example because certain for example, the ability to fly or the ability to see in eyes has developed has evolved on different paths independently in evolution. So all these chaos, emergence, and path dependence are, of course, a sign of complexity, which has other signs, things like hidden links where stuff influences each other and you don't know what it is, feedback loops, tipping points, power laws. These are all signs of complexity, and the modeler has to become careful/suspicious if they can find these, because these are all signs that the models might not be as predictive as they hope. There's another problem: unknown unknowns. Models represent knowledge, right, and experience. There's nothing completely unknown, nothing ever seen before is in a model because nobody has put it in, right? Even in a machine learning model, if you never saw a green cat, then you didn't learn the green cat. And if a green cat shows up, the model doesn't know what to do, right? And a theory of cats has the same problem. So we even can't run sensitivity analysis for these unknown unknowns because we don't know them. So there's a very nice example where you have a turkey, and the turkey lives on a farm, and every day from day 1 to day 99, the farmer comes, brings me food. So the farmer is a really cool dude. Based on Bayesian reasoning, the turkey decides that, over time they build trust, and so the farmer is a really cool guy. But then on day 100, Thanksgiving, as it happens, the farmer kills the turkey. So model was completely wrong. The model had no way of forecasting that because there was nothing in the turkey's experience that would allow the turkey to update their probability of the farmer killing the animal based on Bayesian reasoning and experience. So that's a fundamental limitation. A model cannot deal with that. So this means we can use, for example, models to predict the likelihood of dying from a volcanic eruption or a meteoric impact or maybe a natural pandemic, because these have all been there before. We know about them, and we know a little bit about their probabilities, or we can at least give estimations. But we cannot necessarily say something about the probability of dying from a nuclear war or AI eating us all, or engineered pandemic, because so far it hasn't been there. And interesting is, if we try to do it, for example, the probability of dying or killing all of us from a nuclear war, we can only say something about 70 years roughly, whereas we know that the last meteor was 100,000 million years ago. So that would give a very high probability, because we don't have a lot of data, and the data that we have is very recent. So it's a very interesting book called The Precipice, where Toby Ord tries to still say something about the probabilities here. So was this crane crash on the ship, was this an unknown? Well, not really. People know that the stability of the hook is really crucial. That's why there is a safety factor of 3 in the hook construction. But if the process failure during manufacturing doesn't work, if they just use the wrong materials, then, people know it's a known. That's why they put in the safety factor, but you can't put in a safety factor of 20. Then the hook's so heavy, it doesn't work. So, all right, models. They're not perfect, but what else? What else can we do? Well, we should apply common sense. There is this notion of fast and frugal trees, where when you try to decide whether a patient who shows up in the emergency room should go to intensive care or to a regular unit, you can create a machine learning model that takes into account hundreds of factors and criteria and diagnosis for the patient. But turns out the best result is done by this very simple 3-step decision. Don't ask me what these things exactly mean, but in this case, the high level simple decision tree works better than the detailed model. And doctors would say, haben wir schon immer so gemacht, which is Swabian for we've always done it this way. And so we shouldn't completely discard common sense and become blind model followers, although models are a really good idea. And of course, models evolve over time based on new insights, which is basically what science is, right? So models, they're everywhere. They're ubiquitous. Should have used a more complicated word. The use of model allows us to forecast developments and quantify uncertainties. This is cool. Models make inferencing variables and their effects explicit, and explanatory models help us to understand an issue. Models are the basis for constructive discussion. You can look at a model and say, well, there's an important factor is missing. Let's add that and do a sensitivity analysis. You can't do that based on just feelings, opinions, and just, opinion judgment. I don't think masks work. But of course, the boundary conditions and the limits that we just discussed must be considered. In case of doubt, always crap in, crap out. So this brings me to the end of my talk. If you want to learn more about all of this stuff, you can obviously listen to the podcast. There are several episodes particularly related to this one, to this modeling topic. I also wrote a book last winter, which has a whole chapter on this topic. And of course, I want to thank a bunch of people who helped me improve previous versions of this presentation. Thank you very much, and get in touch and challenge what I talked about.